So now gamma over 2 kappa is integer. So here we have integer, and here we have integer. Naturally, we don't need any branch cuts anymore. Instead, however, we have a pole at point t equals to minus kappa, and this pole is for v function. It's nth order for v function, and it's n+1 order for our solution. So here it is. Point t equals kappa becomes 0 over nth order for v function. So what would be the structure of our contours which define the solution? Well, now, of course, the crucial solution is defined by a simple loop around a pole n+1 order pole minus kappa. The first solution and the second solution is simply, again, the same kind of contour which basically was before when there was a branch cut. However, the solution defined by the second contour is basically not changed in comparison to what we just discussed before, when it was represented by the solution along this loop Hankel type integral. So now it's a closed loop, and its asymptotic will be given again by the vicinity of this minus kappa point. But now the integral itself can be computed exactly. So let's write it down. And the wave function is given by the residue at this pole. So it's 2 pi I times, so that's their n+1 residue, n+1's order residue. So it's 1 over n factorial dn over dt and e to xt times t minus kappa to n minus 1. And the derivative is taken at point t equals minus kappa. Right. So when we perform this n differentiation n times, we'll have to plug in this t equals minus kappa into all our constituent functions. So naturally, after the differentiating, the exponent will simply turn into exponent. So we'll have the whole function will be proportional to e to xt, they're just unavoidable, and t should be put to be equal to minus kappa. So the whole function will behave as x to e to minus x kappa. And we recover the desired exponential decay of our wave function at x tending to plus infinity, which is great. So this is the correct solution. Well, we'll have to check that this condition holds. So let's figure out what's going to happen at point x equal to 0. So let's put x equal to 0 in our derivative, and what we get is the nth derivative of the expression which became a polynomial of n+1 or n-1 order. But if we differentiate the polynomial of n-1's order n times, we get identical 0. So this is the desired result. Our function satisfies both boundary conditions. It vanishes at the origin, and it decays asymptotically at exponentially at x tending to plus infinity. And it all happened only in case when the corresponding factor gamma over 2 kappa is equal to some positive integer, and hence the quantization of energy levels. So we get m alpha over kappa. Let's make a square. And as a result, kappa squared is equal to m squared alpha squared divided by n squared. So energy, the modulus of energy, is equal to m alpha squared divided by 2 n squared. Well, I hope I didn't miss anything. Right, that's it. So here's the demonstration how this counter-integration technique works, I would say, beautifully in just some non-elementary problems in quantum mechanics. So I hope you enjoyed it.